and this is about the defect calculation. Let me first talk about the general structure of the defect. Okay, so this slide I have shown you uh, in the class about molecular dynamic simulations. That in materials, no material is perfect. There are always point defects like the vacancies, or maybe I can use the laser pointer. So this is a laser pointer, right? Okay. Uh, so the vacancies or interstitial or the defect pairs like a Schottky defect or the Frankel defect. So there are lots of the defects. And in the classical and the simulations, we have looked at how the geometry distorts around the defect site. But here, we are interested in the change of the material properties because of the defect. This is particularly important in the semiconductor or the insulators. And it is well known that the optical property and the electrical properties of those the semiconductors are critically depend on the presence of the defect. For instance, the optical properties, certain defects affect absorption and the emission spectra. For instance, here, this is the zinc oxide. The zinc oxide has a very wide Gantt material, 3 electron volts. So, in its perfect crystal, all the light should pass through it. So it's transparent, no color. However, when you grow the zinc oxide crystal in an oxygen deficient environment, then depending on the concentration, it sometimes looks red or sometimes it looks green. Okay, so the color, it takes the color because of the concentration of the oxygen vacancy. And also the same is true for the strontium titanium oxide. And also in the case of TiO, the TiO is an excellent photocatalyst. Okay, it is a very efficient photolytic convergence efficiency for the oxygen evolution reaction is very high in this material. But the only drawback of this material is that its band gap is so wide. It's a 3 electron volt. Therefore, all the visible light is just passed through it. It does not observe the visible light. So in order to enhance those absorption of the visible light, sometimes people introduce the defect or the dopants, okay, and they produce the defect levels within the band gap, which observe the visible light. Okay, so those are the change of the optical property, and also it affects the electrical property. Okay, and it is well known that non-stoichiometric defect or the vacancies increases conductivity. So TiO2, zinc oxide, or indium oxide, all of them are band gap more than 1 over 2 electron volts. Therefore, it should be insulators in its perfect form. But when you introduce the vacancies, then it is very good N-type semiconductor or the conductor. Okay, and it is well known that those ITO indium tin doped indium oxide are very good conductors. And also the external dopant affect the ionic conductivity, like yttrium doped strontium stabilized zirconia. In this case, they introduce the dopant, introduce oxygen vacancy, which accelerate the diffusion of the oxygen atoms. And also the defect levels in the band gap play as the recombination center of the electron in the hole. Okay, so electrons in the conduction band and the hole in the valence band, they are somehow recombined at the defect site. Okay, and so they are annihilated. So these are the defects that critically affect the various properties in the semiconductor or the insulators. All right, so and all of these changes actually comes from those specific or characteristic defect level introduced within the band gap of the material, and we'll discuss about that. And here we will specifically use the example of the magnesium oxide (MgO) or rock solid structure, which is is very good, well-known, standard, or very well-known the insulators with the band gap of almost like 7 or 8 electron volt. Okay, so here in the magnesium oxide MgO, we want to calculate the oxygen vacancy. The first thing that we notice is that by introducing such an oxygen vacancy or the defect, you are break the periodicity or the symmetry, translation symmetry of the crystal. Okay, so the crystal by definition, it is invariant under the certain translation operation. However, by introducing the oxygen vacancy, you are breaking it. Therefore, there's no periodicity in the defective solid. However, since we have to impose the periodic boundary condition within the calculations, what we are doing here is that we artificially repeat the vacancy, in a certain regular patterns, and such that one supercell, there is a supercell, and the one defect is included in each supercell. Okay, so this supercell typically, it depends on the computation or the defect type, but it's better to take the smaller supercell. But the smaller supercell always and has an artificial interaction between the defect. Therefore, sometimes it gives you the wrong result. Therefore, there's some reasonable size of the superset that we will discuss later about the more specifically about the superset size test. But here, for the convenience, we take the 64 atom supercell, which consists of the 64 or 32 magnesium and oxygen atoms, and its cell is the cubic cell. Okay, and its lattice parameter is simply the 2 times of the lattice parameter of the primitive magnesium oxide, or not primitive, but a conventional magnesium oxide. Okay, so and about those computational parameters like cutoff energy or K-point selection, what we're doing here is that we basically follow the result in the Berg test that maybe in the last class you have seen that by change the cutoff energy or the K-point, we have seen this energy converges to a certain value. All right, so we use the similar cutoff energy, but sometimes, very rarely, you have to change the different the cutoff energy. But as a first choice, you can take the cutoff energy that you have obtained from the Berg test. And about the K-point, it actually reduced by the reciprocally with respect to the lattice parameter. That is to say, for the conventional cubic cell, if the 4x4x4 supercell, 4x4x4 K-point was enough, then in this 2x2x2 supercell, then you are reduce this K-point density by, inversely to the lattice parameter, that you reduce this K-point to 2x2x2. All right. So those things that you are checking before you start your computation, and also even though the starting structure is from the well-converged or the most stable position in the Berg, by introducing the vacancy, those atoms nearby the vacancy should have a different equilibrium position, right? So in order to find the position, we have to relax it with the options that is included in the program, and you can see that here that for about 5 or 6 times of the ionic steps, you have arrived this convergence in the energy. That is to say, all the atoms are fully relaxed. And if you check the length that each ion has moved, then this is the oxygen vacancy. The oxygen vacancy in the MgO is called F center, or usually in general, and the anion vacancy in ion solid is called F center. This F comes from the Farbe, the German name of the color. Okay, because the vacancies usually induce certain coloring of the material. Okay. So here we are interested in the anion vacancy or the oxygen vacancy. So if there is oxygen vacancy, then there are, the magnesium atoms are the first neighbors, and they relax just slightly differently, slightly move outward by about 0.02 angstrom, which is really a tiny amount of the length. And also the second neighbor, it is almost, does not move, minus 10.004 angstrom. So basically, its relaxation is limited to those first and second neighbors in this case. All right, but for the different defect, we have the length of the relaxation. All right, so and you can actually plot the band structure of this supercell. See, this is this cubic supercell, so you can take this K and L point as a cubic cell. And this is the defect-free the band structure, okay? And this red one are occupied band, and this green one are unoccupied band, okay? So its band gap, you can see this direct band gap, the gamma to gamma, its band gap is 4.6 electron volt, which is actually about half of the experimental band gap of the 7.78 electron volt. So this is the well-known underestimation of the band gap in the semi-local function. Okay, and also you can see that there is many bands are actually crossing within this the Brillouin zone. This is because you have the supercell, and therefore the band structure is actually folded into this first Brillouin zone. So that's why you are looking at many spaghettis over the bands within this Brillouin zone. Okay, compared to the primitive cell. And this is dense state, and you can say this is Fermi level, okay, and this is the balance, and this is conduction. On the other hand, when you introduce the oxygen vacancy and you plot the band structure from the K to gamma to L, then you can see that the occupied and unoccupied balance band looks more or less similar to the perfect crystal. But one distinct difference is that there is within the band gap, there is one flat band that develops, and these are occupied by 2 electrons. You can see this from the color. Okay, so the Fermi level is actually between this the red one and green one. So the flat band is occupied, and in the dense state, you can identify this flat band by the sharp peak within the band gap. All right. So this is the characteristic of the defect, and so we call them as the defect level. Okay, electron structure that is associated with the defect. Okay, let's look at the distribution of this state more in detail. And this if you the plot this isosurface or distribution of the wave function, then in the balance top, this balance band maximum is more or less delocalized. Okay, so this is delocalized, and so it dispersed throughout the crystal, and therefore this is similar to the balance band maximum of the original perfect crystal. Okay, and also if you look at the plot of conduction band at the bottom, even though there is the vacancy and the wave functions are slightly modified around this defect, its overall distribution is similar. Okay, so I did not say the details, but this red one, the color is the maximum intensity or the maximum probability of the wave function. So and so the electrons are concentrated at each atom. Okay, and so this balance band maximum and the conduction band minimum are actually very similar to those in perfect crystal and not much affected by the presence of the defect. On the other hand, if you plot these states at in the mid gap, then it is concentrated at the defect site. Okay, and if you plot 3-dimensionally, then this is isosurface of the defect. It's like a S orbital that is centered around the oxygen vacancy site. Okay, so S-like state. So this is why this flat band always comes from the localized wave function. All right, and also by plotting one by one, you can see also that this 3 band here, just above the conduction band, the minimum at the gamma point, is if you plot it, then it looks like a P-like band, P-like state. It has one node here, but still concentrated around the oxygen vacancy site. Okay, so this is why these states are called the defect state. Okay, so they are concentrated or localized at the defect site. All right, and so this state, this oxygen vacancy site, the S-like orbital, it takes up the 2 electrons, is occupied by the 2 electrons. So this is a neutral in the sense that its nominal charge distribution is similar to the crystal. In the crystal, this site was occupied by oxygen. Okay, so oxygen takes up the 2 electrons from the magnesium. All right, so oxygen 2- and the magnesium 2+. even though there is an oxygen vacancy, still it has the 2 electrons here at this site. It is effectively 2 minus charge. All right, very surprising. Even though there's no oxygen, you know, this site behaves like a 2 minus site. Okay, so so electrically, this is a neutral state because it is a whole crystal. All those magnesium atoms are 2 plus, and all those oxygen and this vacancy is effectively 2 minus charge. Therefore, all these the charge balances are perfect, and so this is called oxygen vacancy, neutral oxygen vacancy, or VO and 0. Okay, this is the vacancy and oxygen, and 0 means the neutral charge state. Or in the defect chemistry, in the Craig-Vink notation, this is VOX. They say this is VOX. So this is the electrically neutral state. All right. Okay. So one thing that you may remember is that this defect level, this energy position. So there is a defect level, but this energy position is actually does not correspond to the energy level of the charge state. The energy level of the charge state means that the energy you needed to take out the electrons from the defect site, it does not necessarily or usually different from the defect level, energy level from here. But the precise value, for the precise value, we will have to calculate total energy that we will discuss later. All right, so the important thing is that when you introduce oxygen vacancy in an insulator, semiconductors, their defect level develops within the band gap. Okay, and it is a big change in the band gap, in the electrical property or optical property. Depending on the energy position of the defect level, we categorize defect level in different terms. In the case of the deep level, which corresponds to the previous case where this defect level is well in the middle of the band gap, or deep inside the band gap. In this case, defect level is very clear and is distinctive from the balance or conduction band. However, sometimes the shallow defect is developed, which means that this defect level is very close to the balance band or conduction band. All right, and this conduction band, if it is close and if it is filled, it is occupied by the electrons, then it plays as a donor. The most well-known example is the phosphorus in the silicon. All right, when you dope the phosphorus in the silicon, it produces electron carrier. Right, and we call them as a shallow impurity. That is to say, the charges at the donor site, they are activated to the conduction band and it conduct the electrons. All right. And also this the level defect level that is close to conduct the balance band maximum, and if it is empty, then it is act as acceptor, right? The electrons at the valence band, they can be excited into the acceptor level and thereby creating hole at the valence band maximum. All right. So and sometimes the defect levels are the resonant. I mean, it is well inside the conduction or valence band, and so they does not appear within the band gap. All right. So we call in this case the resonant with the delocalized conduction or valence band. All right. So, but the problem is that in these two cases, technically, it is quite difficult to resolve. In these two cases, we will come back to this point later, because when you use the small spot set, all right, okay, and the shallow states are well described by the so-called effective method theory, and they are usually delocalized over a few nanometers, right? So its wave function size is at least several tenths of the angstrom. On the other hand, in this case, the deep level, if you plot the wave function, then you can see that they are more or less confined within a few atoms or maybe a few angstrom, right? So within the less than 1 nanometer. This is the deep level, but for the shallow level, the wave function is more delocalized. Okay, so that was the neutral, the vacancy, the basic starting point when you study the defect. You can also study the defects that is charged. That is to say, the electrons are not actually taking up the 2 the defect level does not have the 2 electrons. So in the first case, we have seen just before that the neutral option vacancy and their defect level and 2 electrons are occupied, right? And you can actually charge or remove the electrons from this option vacancy by changing the number of the electrons used in the computation. So in the first case, the electron was 250, okay, at the neutral state. So by default, this number of the electron is used. But you can intentionally reduce this number by 1, okay? Then you have 1 less electron from your system, which means that you are occupying only 1 electron at this top level, all right, because you have the 1 less electron, all right? And therefore, the 1 electron is occupied, which is shown up here, and the other electron is actually emptied up, right? So, and it is because of this, the spin-up, and this, let's say that this is spin-up occupied by spin-up electron, and this is unoccupied by the downspin. And then in this case, because of the spin polarization, energy level is actually split, right? So in this case, you have to actually turn on those spin polarization option, right? So you will learn in the next class about how to turn on this spin polarization. Anyway, so this is a singly ionized case, right? So only 1 electron is occupying this defect level. And so the charge state is 1 plus. The neutral was 2 electrons, so 1 less electron. This is PO plus over Prager-Pinker notation, PO dot, because it has a hole, right? Or you can remove 1 further electron, and by reducing this n electron to 248, and in this case it's doubly ionized defect level, or VO2 plus, or VO double dot. Okay, so you can actually calculate on this charge defect by simply reducing the number of the electrons you use in the computation. Okay, so and the doubly ionized case, you can see that the defect level is completely unoccupied, and this appear as color blue, green color. Okay, and if you look at this relaxation around the defect level in the neutral state, compared to the equilibrium position at the bulk, you have seen that this relaxation was quite small. Okay, the first shell moves only 0.02 angstrom. The second shell, is minimal. But in this case, the singly ionized case, you can see that the first shell, the magnesium atoms, are actually relaxed outward by as much as 0.1 angstrom, right? Which is actually quite significant. In the atomic scale, 0.1 angstrom is quite significant. And the second shell, oxygen, is relaxed inward or toward oxygen vacancy by 0.03 angstrom, right? And the VO2 plus, you have the further relaxation, and the first shell pushes out by 0.17 angstrom, and second shell comes inward, relaxed inward by 0.07 angstrom, which is actually almost the double of this relaxation that you found for single charged case. So why this the direction of this relaxation? This is because of the charge. Okay, so this is oxygen vacancy in the plus charge or plus charge. You have the plus charge, and these magnesium atoms are effectively plus charged. Therefore, this plus repulsive interaction, and therefore magnesium atoms are pushed outward. On the other hand, oxygen atoms are minus charged. Therefore, they are pulled in toward the vacant site. Okay, so this relaxation pattern, is basically can be explained by the charge interaction, electrostatic interaction. All right. Okay. So we have seen the basic, the defect and neutral and charged, and what kind of defect level are induced within the bandgap. So one important thing that is related to the defect is the defect formation energy. This is basically energy, then you create a defect in the solid, right? Which is the determine essential thermodynamics of this point defect. So if there's any question, please, raise your hand at any time. So everything's clear? Okay. All right. Okay, so let's first define this Gibbs energy of the defect formation. So as I mentioned, this is the energy that you create auction on certain vacancy. Let's say this is auction vacancy specifically, and with the charge state of the Q. Okay, so this means that you are moving the auction atom to a certain environment. Okay, which is because this is this is not an isolated system. This is the thermodynamically connected to the environment. Okay, so you are taking this one auction from the lattice and you're moving to the surrounding or reservoir. And also by changing the number of the electrons, you are actually taking out or pulling in electrons to and from the environment. Okay, so the Gibbs free energy is the energy difference between the perfect, when there is no defect, and when there is a defect of this type. Okay, so and this here, the Gibbs energy of the defective system is consists of the energy of the defective cell. Okay, as shown here, and also since you have to move this auction to the surrounding, which is actually controlled by the oxygen chemical potential. So you have to add up the chemical potential of the oxygen. And also since you have removed a Q number of the electrons to a certain environment, and this electron is the chemical potential is controlled by the Fermi level. Okay, so you have to add up the Q plus mu E, right? So this blue one defines the energy or Gibbs energy of this defective cell. All right, remember that you have to move this oxygen to the environment and also the electron to the environment. That controls this oxygen chemical potential and the electron chemical potential. All right, and the electron chemical potential is always this is called the Fermi energy of the system. All right, and so the Gibbs free energy is the difference from this energy of the defective cell from the perfect cell. All right, so these two difference. And here, the energy difference of the defective cell and the perfect cell, it actually consists of, by definition, the change in the internal energy minus T times entropy change plus P delta V. All right, because the G Gibbs energy is the U minus Ts plus PV, and we are considering this reservoir is controlled by a certain temperature and certain pressure. All right. So here, okay, and remember that what we get from the BOSP calculation is actually internal energy, or here the U. Okay. Therefore, when you read the energy from the BOSP calculation, is actually total energy is corresponding to the change of the internal energy. So by simply read the energy and take the difference of the charge, the defect, and the perfect cell, then you are getting this change in the internal energy. All right, this is the most simplest part. Second, the entropy contribution. This is usually the entropy change between the perfect cell and defective cell. And here at the moment, we are ignoring those configuration entropy of the defect. So creating the defect or removing the one oxygen has various choices, right? So itself has some of the entropy contribution. But here we are ignoring that configuration entropy, and we only consider the thermal entropy or thermal vibrations. Okay, so in this case, even though it is small, but it's more finite, but it's quite small. Therefore, we can actually usually ignore this entropy change difference between perfect and the defective cell. So if you read, for example, this reference, it is about 0.1 electron volt. So it is, unless you are interested in chemical accuracy, then this is something that you can ignore. All right, And the last term, P delta V. So this is comes from the volume change due to the defect. All right. So when you make the defect, it will slightly shrink, and the magnitude is well at the most 10 cubic angstrom. Right. So therefore, we're putting this number and converting this pressure, then it is about 10 to the minus 10 electron volt times pressure in Pascal. So we are interested in about the range of the 1 or 0.1 electron volts. Therefore, unless your pressure is extremely high, like several hundreds of gigapascal, then this P delta V is completely negligible. All right. So in conclusion, you can ignore this T delta S and P delta V, and so conveniently this free energy change is actually equivalent to internal energy difference between the defective cell and the perfect cell, which you can easily get from the possible calculations. All right. All right. So and we still have the other part, the oxygen chemical potential plus Fermi level. One thing in the technically, one important thing is that when you compute these two quantities in the defect calculations, then every setting should be the same in both calculations. The K point and also the cutoff energy and every pseudo potential selection, everything should be the same in both calculations. All right, unless the small difference in this can be actually scaled up because the superset calculations. Therefore, this error, small tiny error, can scale up, right? So therefore, in order to have the difference that is actually related just with the defect, you always have to maintain the same computational setting in both calculations. That is one thing that is really important, but sometimes can be forgotten. Okay. Okay, so so we have this part, and now we will discuss about this oxygen chemical potential, and this formula that is already given, so we will talk about this oxygen chemical potential. Okay. So about the oxygen chemical potential. So it depends on the environment, what kind of environment you have, right? And so our system is magnesium oxide and one defect, and you have to consider another environment, right? So basically you have the magnesium oxide, okay? And so in order to define the chemical potential of the oxygen, actually you have one further phase that is equilibrated with this MgO that will define the oxygen chemical potential. All right. So here there are two extreme limits. The first one is the so-called oxygen leach limit. In this case, your magnesium oxide is actually surrounded by or at equilibrium with the oxygen gas with a certain temperature and certain pressure. All right. So it is enough oxygen, so much enough oxygen, so it is or oxidizing condition. So in this case, oxygen chemical potential. So this oxygen gas actually defines oxygen chemical potential, right? Maybe you have seen this in your thermodynamics class. And so this oxygen chemical potential, atomic oxygen chemical potential, is actually half of this O2, the chemical potential of the O2 molecule. All right. And this environment itself defines the chemical potential of the O2 molecule, all right? And by assuming the ideal gas, well, most of the gas actually follows the ideal gas rule, and this oxygen chemical potential at the temperature T and the pressure the P is in reference to the standard pressure P naught. This is usually 1 atm. It is has this additive term of the log P over PO. Okay, so the pressure ratio, and this P is oxygen to partial rate pressure. And another thing is that at the 0 Kelvin, when temperature is very low, then all the atoms or the molecules are actually standing still. At 0 Kelvin, there's no kinetic motion. So therefore, there's no, the pressure or no motion, just stay there. Therefore, in this case, the natural choice of this oxygen chemical potential is simply the total energy or internal energy of the O2 molecule, right? So which we get from the computation, all right? So we have this value at 0 Kelvin at pressure P. And so at the general, the T and the P, this is standard pressure. So by increasing the temperature from the 0 Kelvin to temperature T, we actually add up the enthalpy and the entropy contribution, delta H minus T delta S. Okay, these are the enthalpy and the entropy change per molecule between T and the Kp0. And this is actually available for the thermochemical table. So you can calculate it theoretically, but also, thermodynamics, experimentally, they are well known. Okay, and if you look at this reference, then when this P standard pressure is 1 atm, this half of this H minus T delta S is as follows, right? From this 100 Kelvin to 1000 Kelvin, it can go up to 1 electron volt, right? So depending on the temperature you have, like 400, 500, you can just simply choose this one of these values, all right? And it will give you the chemical potential at T and the PO, right? Standard pressure. And in general, at the T and the P, you can simply add the partial pressure part, okay? And it will give you, in general, the oxygen chemical potential at the T and the P, all right? Or simply, so when you are really concerned about this oxygen pressure and the oxygen chemical dependence on the temperature and the pressure, then you have to use this, the original definition. But just for simplicity, we usually, sometimes you simply put this oxygen chemical potential as the half of the total energy of the O2 molecule, which we get from the calculation. And within the GGA, this is, or simply, this is the about minus 4.93 electron volt. No, this is the actually experimental value. Okay, so this is theoretical value of this amount. Okay, but one thing that we notice is that this O2 binding energy, experimental binding of the O2 molecule. So this is the energy then you need to pull apart this oxygen molecule into the two separated oxygen atoms. This is actually overestimated in GGA. In theoretically, it is about 6.7 or 6 electron volt versus experimental value of the 5.23 electron volt. This means that O2 molecular binding energy. This is overbinding in the GGA calculations. All right. So which actually reduces the formation energy of the oxygen vacancy, or increases it, or make it easier to create oxygen vacancy theoretically. So sometimes when you really care about this oxygen chemical potential, you have to actually correct this overestimation in the O2 binding energy with the experimental value when you're really serious about oxygen chemical potential. And another thing is that in using the partial pressure to control the chemical potential, right? So by changing the chemical partial pressure, you are actually controlling the oxygen chemical potential. Here we are assuming that equilibrium condition. So all these oxygen vacancy or defect concentrations are at equilibrium with the environment. But in many cases, such a condition is not hardly achieved. For instance, molecular beam epitaxis is a highly non-equilibrium growth process, and therefore we have lots of the much more different defect concentrations in your system, right? But only at the high temperature and MOCVD growth condition, for example, in this case the equilibrium is very well achieved. Okay, so this oxygen chemical, the pressure, the partial pressure, sometimes it does not give the actual concentration in experiment because of non-equilibrium condition. in the actual sample growth. All right, so another limit is metal-rich condition. In this case, the environment is, instead of the oxygen gas, it is metal, magnesium metal. So this phase, so MgO is in equilibrium with the magnesium metal. All right, so in this case, the chemical potential of the magnesium is simply the energy of the solid phase, the magnesium energy. So here, of course, it should be the Gibbs-free energy, but similar to the previous discussion, that entropy and the volume change pressure part is actually negligible. So by neglecting it, we are just keeping this internal energy part. Okay, so the magnesium chemical potential is fixed to the energy of the magnesium metal, and also since we have the magnesium oxide here, therefore the chemical potential of the Mg and oxygen should be equal to the chemical potential of the MgO, or the total energy of the MgO. All right. So from this, oxygen chemical potential is now recalculated from the difference of these two values, and it is minus 10.42 electron volt. So compared with the previous oxygen-rich case, in this case, oxygen chemical potential was about minus 5 electron volt, but in the metal-rich case, we have minus 10 electron volt, right? So in this environment, oxygen chemical potential is much lower, which means that it tries to, the oxygen is likely to go to the this magnesium side, or try to escape from the material, which will naturally induce more concentration of the defect. All right. Okay. So this metal-rich limit, or the reducing condition, you can calculate this chemical potential in this way. All right. In the case of a ternary compound, for instance, strontium titanium oxide, you have the three elements: strontium, titanium, and oxygen, right? So in order to extract this oxygen chemical potential, you need a three-phase equilibrium. So in the previous case, you have only two elements, magnesium and oxygen. Therefore, by this equilibrium between the two phases is enough to define the chemical potential. But in this case, you have the one more component, which means that you need three-phase equilibrium to specify the chemical potential. So in this triangle phase diagram, so strontium, titanium, and oxygen, so there are several vertex points which defines the three-phase equilibrium. For instance, in this point A, here this is the equilibrium with strontium oxygen and O2 gas, right? So therefore, the chemical potential of strontium and oxygen is equal to chemical potential of the strontium oxide, and also the oxygen chemical potential is the oxygen chemical potential of the O2 gas. All right. So from these two and these three, you have this oxygen chemical potential. Or in this case, if your environment is close to this B point, in this case, it is equilibrium between the O2 gas and TiO2. All right. So depending on your environment, you can choose the different choice of the chemical potential. All right. Okay. So it is not easy. It is quite difficult to actually match exactly the experimental condition and the position at the chemical potential. So we have just some certain boundary of the oxygen chemical potential. All right. Okay. So and here one comment is that in the case of the oxygen and the titanium, so for instance, if you are interested in the material TiO2, so in this case, when this material is in equilibrium with the metal-rich condition, the metal-rich condition in the previous okay, yeah, it's a mistake. All right. So in the previous case, the magnesium-rich condition was in equilibrium with the pure magnesium, right? So you may think that in the TiO2 metal-rich condition may correspond to the metallic titanium, but this is not the case, because between the Ti and the TiO2, there are several phases of the understoichiometric condition, understoichiometric or less stoichiometric than TiO2. For instance, most close here you have the Ti2 or 3, or more closely there's so-called the magnetic phase Ti407 or Ti509, which is very close in compositional ratio to TiO2. So metal-rich condition in this case should be considered instead of the titanium metal. You have to consider this Ti2, 3, or the magnetic phases. All right. So define this chemical potential is quite important, or you have to consider this stable phases along the phase diagram. All right. Okay. And the correction term. So this is about the artifact that comes from the supercell, the final supercell size. Okay, so here in the previous section, we have seen that this formation energy gives a defect, gives free energy of the defect formation is calculated as the energy of the defective cell and the perfect cell, and also optional chemical potential, and also the Fermi level. Here, the Fermi level is redefined with respect to the balance band maximum. Okay, so defect level with respect to the balance band, this epsilon f or the Fermi level ranges from the 0. 0 means balance band maximum, and up to the energy gap. The Eg is the correspond to the conduction band maximum. All right. So this is the definition. Because of the finite cell effect, actually two terms should be added here. One is the correction energy, this ECORR. This is the electrostatic interaction between the charged defect. So in the really big superset, which should correspond to the actual system, in that case, there's no interaction between the defect because they are so far away. All right, but in our case, we are repeating them in a small supercell. Therefore, there is a electrostatic interaction between. Okay, so let's come back to this correction energy. So this reflects the electrostatic interaction that's corrected, and it reflects the interaction of the between the charge defect, and also this PA. This is so-called potential alignment. I will explain that shortly. Okay, so first about the electrostatic interaction. So what does this mean? Okay, so in the plane wave formalism, the period boundary condition, you can calculate this Coulombic potential, Coulomb potential, very conveniently by making use of the Fourier transform, okay, rather than real space. So in a Fourier space, when the G is the reciprocal lattice vector, that is Fourier component of the Coulomb interaction is given by 8 pi times of the corresponding component of the charge density divided by G square. Okay, so this is okay, except for G equals 0. The reciprocal lattice also includes the gamma point, or G equals 0. All right. So in this case, you have, this divergence in the denominator. All right. But actually, for the neutral system, this charge, this low 0 means the actual average charge in your system, and usually it is neutral. So therefore, this low 0 is 0. Therefore, this is 0 divided by 0, and this is indefinite. And actually, you can actually set to this 0. Actually, this is not trivial, but actually my advisor, my PhD advisor, Professor Jizunim, actually contributed to this finding that you can actually safely set this V0 as 0. He have proved it, okay? So for the neutral system, this V0 is 0, all right? They said that it can be proved. But for the charge system, we have the low 0 is not 0 because we have the charge system. So average charge is not 0. And so this is a finite number divided by 0, so it will diverge. Okay, so this cannot be computed. So to overcome this, the V0 by convention, it is enforced to be 0. Okay, which means that you are actually using instead of in the case of charge system, your charge is low 0 is 0. Meaning that you are actually introducing the uniform background charge, which we call UBC, with the opposite charge sign is introduced. For example, in this periodic cell, these plus charges are the oxygen vacancy, let's say, VO plus. And in order to have this neutral charge, you have uniform background charge, minus charge with the same amount, but it is completely constant throughout the system. All right. So by having this uniform background charge, it will not, since it is uniform, it will not affect any, this dynamics of the electrons. Okay, but it will effectively nullify this charge, the defect charge, and therefore you can compute this by setting this V0 as 0. Okay, so this is uniform. So actual charge distribution is that rather than the really isolated charge you have, in addition to that, you have this uniform background charge. Okay. So for the large, the lattice parameter UBC is diluted, and so the result will converge to isolated, which we want to describe in the calculations. And one thing is that this uniform background charge, this is introduced only in the potential, and the charge density is, on the other hand, when you calculate charge density, this is completely removed. It's not considered. All right, therefore, this means that L goes to the infinite. And so what we want to try to describe is that in the really, really large cell, you have this isolated system, which is we want to calculate. But since we are having the finite or maybe the small lattice parameter, there is a difference between two calculations, isolated charge distribution versus periodic charge distribution. So this correction energy is actually the difference between the two. The energy, the static energy of the isolated system minus the energy of the periodic system. All right. So this defines the correction energy within the electrostatic interaction. So how can we correct this? Many people actually contributed to effectively reducing this spurious interaction between the charged cell. And one that is most widely used is the scheme that was developed by the Markov and Payne many years ago, 20 years ago, and they have simplified or they have expanded this correction energy with respect to the 1 over L, and they have found that the reading term is the monopole interaction, and the second reading term is the monopole and the quadrupole interaction term. Okay, so Q square and the Q times Q. Q is the quadrupole, the second moment of defect charge distribution. All right, and so these two terms are called the MP1 and the MP2. Okay, Markov and Payne. Okay, so this is the exact for the molecular system. So when you have the completely isolated system, this is the perfect, this is the accurate. But in the case of the solid, the defect charge distribution is not really localized. It's actually somehow mixed together with the charge density of the solid, and therefore it is there's no clear distinction between the localized defect charge and the charges of the periodic system. So it is an approximation. It cannot remove completely this finite set size effect. Okay, so the second is the potential alignment. So why is that? So it started from by comparing this band structure of the periodic system, the completely clean system, the defective system. So this is neutral defect. There's no charge, but when you compare this balance band maximum, it is slightly lower than the balance band maximum of the clean supercell. Okay, so and if you plot this potential difference between the defective and the clean cell, and with respect to the difference from the around the defect site, then you can see that it's far away from the defect site. Still, you have the finite difference in the potential between the defective and the clean cell. It does not really converge to the zero, right? So this actually comes from, and this actually raises the energy of the defective cell of charge Q by Q times PA, right? So this comes because in the same thing, your potential, the VQ in any cell, we always set this VQ V0 as 0, which means that this potential average is always 0. Therefore, when you have the defect, around the defect site, we have a very high potential. So in order to compensate this high potential, we have this lowering of the potential that is away from the defect site. All right. So the correction of this misalignment is called the potential alignment. So this can be reflected. This can be calculated most handily by looking at this the so-called the electrostatic potential at the core site of the core state. So in the Boss calculator, you will learn in the next class how to get these numbers. But by looking at these potential values at the core state, you can actually trace this potential variation at each atomic site. And so, for instance, if you have this 64 supercell, the smallest supercell that we have, in this case, is away from the defect. You have this potential, misalignment by 0.09 electron volt. But as you increase your supercell size, this is gradually reduced, and it will eventually converge to 0. Okay, so for the final cell, you still have this some of the difference in the potential value. Okay, so by tracing this energy level change, you can actually can get this potential alignment value. Okay, so we have discussed the two correction scheme. The one is the electrostatic correction. Here is ECOR and the potential alignment. Okay, and including this is supposed to reduce the cell size effect. In order to trace that more systematically, what we do is that usually by changing the lattice parameter or the supercell length, we get this different formation energy. All right, and fit this value with this the simple formula and extrapolate it to L equals to infinite. All right. So here, in the case of the MgO, we have the 3 supercell, 64 supercell, 64 atom supercell, and the 216 supercell, and the 450 12 atom supercell. We calculate on the 3 supercell, and these are the formation energy. Okay, this is is a bare energy. There's no correction. All right, and we fit this 3 point using this formula here. Okay, it is a little bit does not make sense to the fit this 3 point with the 3 parameters. But anyway, if you fit this, then by taking this L equals infinite, then you have this value, all right, here. So you can see that, it has a very strong. So for instance, for the 64 atom supercell, if you have this energy of 11.2, then actually the converged value should be 11.9. There is a huge difference, okay? So you have a very strong self-dependence in the formation energy, especially when it is highly charged, all right? On the other hand, for this, you can actually correct this using this the scheme that we have learned just before, like the Markov-Payne scheme and also the MPPA potential alignment. Then we have much less cell size dependence. Okay, and already for the 64 atom, we have the well-converged result, and at the worst, we have only 0.3 electron volts difference. All right, so this is the correction scheme works quite well. And this is the LG is actually a Lenny-Jungo scheme, which is the scheme that is quite favored. All right, and this is 2+ case, and in the case of the neutral cell, you can see that basically there is no cell size correction. Okay, so without any correction, it does not change the result that much because of the neutral cell. But in the case of the 1+, we have the slight difference, and the 2+, we have a quite strong dependence on the cell size. All right, so you can see that for the highly charged system, we certainly have to correct your result and have to correct the cell size effect. And other charge correction schemes are maybe this is the most the advanced or the modern method. There's suggested by the Freisel and Neugebauer and Christian van der Waal. And in this case, they have modeled the distribution of the defect charge and developed a quite advanced method. And actually, in our group, we are using this correction scheme. It works quite well. All right, I think that can conclude this first part, and let's have the break, about the 15-minute break, and come back here about 25. Okay, yeah. And if you have any question, please come to me. Yeah, brilliant.
지금 화면 설정을 좀 바꿔봤는데 화면 잘 비추는지 확인 부탁드립니다.
잠시만. 그 트랜지션 레벨 다이어그램 맞죠?
네,
네,
맞아요.
네, 잘 보입니다.
네, 감사합니다.
Okay, shall we continue? Everybody take a rest, you know?
Yes, we are ready.
자네 말고. Not you. Okay, so as inside, so everybody is there. Are you all awake? I cannot see you. Okay, let's continue. All right, so we have so far we have discussed about the defect and charge defect and its energy and how to correct it correct the final set size effect. Okay, so one of the question from the student was that I realized that I missed this comment that what we want to calculate is one isolated defect. Okay, so sometimes defects are so dense that they are together in a very close distance, but that's not our purpose here. But here what we want is that this defect is very dilute. So at least they are several nanometers away from each other. Okay, so in this case, the defect is isolated, and so that's what we want to simulate in this calculation. So that's why we needed to correct this periodic cell size effect. Okay, so using this Gibbs free energy that we have just discussed, we can calculate the so-called transition level diagram. So we have calculated the oxygen vacancy formation energy, right, using this formula here. And here one variable is the Fermi level position. This is a variable, so we have not yet discussed how to fix this, the Fermi level. And this, the corrected total energy reflects this cell size effect and also the potential alignment, which is also comes from the finite cell size. Okay, so then we have this oxygen vacancy. When it is neutral, you can see that since Q is 0, it is not affected by the Fermi level position, right? So this Fermi level, and here is ranges from the 0 to 4.6 electron volt about, which is the correspond the band gap of the theoretical band gap of the magnesium oxide. Okay, so and this is so the neutral oxygen vacancy, it is flat, it's constant throughout the Fermi level range. On the other hand, the VO1 plus, you have this Q equals 1. Therefore, it is linear with respect to linearly depends on the Fermi level. So you have this linear line here, VO1 plus, and the VO2 plus, you have your slope is doubled, right? Because Q is increases from 1 to 2, so you have the double the slope. All right. Okay, so then you collected these three energy for your neutral, for your 1 plus, for your 2 plus in one diagram. So what you can see is that this is Gibbs free energy, right? And what we know is that the Gibbs free energy always, the system always tries to minimize the Gibbs free energy. So the charge state, it actually takes the only those lowest free energy state. So therefore, when this Fermi level is ranges from the 0 to 1.5, then its charge state is VO2 plus. All right, and then between the 1.5 to 2.5, then VO1 plus is now the lowest, and above the 2.6, now the neutral vacancy is the most stable. Okay, so the charge state of the same defect, it actually depends on the Fermi level position. At the lower Fermi level, it tends to be positively charged. And at the higher Fermi level, it tends to be neutral or the negatively charged state, right? Which can be understood because the Fermi level is the nothing but the chemical potential of the electron. So the chemical potential of electron, when it is lower, then it usually takes the electrons from the defect to the lowest, the lower potential that is of the environment. Okay, so this is usually the positively charged, and this side is a negatively charged state. And so this transition level, when transition energy, when it is transition from the 2 plus 1 plus state, this is 1.5 electron volt, and 1 plus and 0 is 2.6 electron volt. So these energy are called the transition level, right? So when the Fermi level crosses this transition level, then it changes charge state. The defects change charge state. All right? Okay. And so, and one thing that you can notice is that, so in the beginning, right? So in the beginning, we have calculated this defect level, and the defect level in the neutral defect level was about the 2.5 electron volt above the Fermi level. But when you calculate actually the transition level, then this first ionization or actually this is pretty similar, 2.6 electron volts. So this is similar, but usually, in general, this transition level, it does not necessarily correspond to defect level that you read from the eigenvalue. All right. So that's why. But this is the transition level, right? And so this is that's why we have to calculate this formation energy, and rather than reading the eigenvalue of the defect level. Okay, so before moving on, we needed to mention about the band gap correction. Because this charge transition level is sensitive to the Fermi level position, which means that it also depends on the Fermi level and the band gap, right? So for instance, this is the band gap of the LDA. Then you have this transition diagram, transition level diagram of the D plus and D0, right? And so this is the LDA. And so if in an experiment, it can be widened to the balance band is lower and the conduction band is higher. All right. So in this case, there are two cases of the possible. The one is that this defect level is stayed there, and you simply just change or shift the balance band downwards or conduction band upward, right? But the same transition level. Or on the other hand, this transition level actually can follow to the band gap increase, and now the neutral state is much higher than this. Therefore, the band gap correction, the effect of the band gap correction is that it can shift the transition level with respect to balance band or conduction band, or it can also change the formation energy. All right. So band gap correction is always necessary. Actually, it's quite critical. But one thing that one trick or one simple way to reflect the band gap correction is to use this invariance of so-called invariance of transition level, and it was found in this paper that they compared the defect level, transition level of the several semi-local functional, several materials using the semi-local functional and hybrid functional. Hybrid functional gives you the right band gap, right? So it's supposed to be accurate. And what they found is that this transition level is when they are referenced to the common level, then this defect level is actually invariant. The same. Only the balance and the conduction band is a shift. All right. So this means that by simply calculating the band gap, the change, not the band gap change, but the balance band and the conduction band shift, then you can simply shift your transition level and reflect this correct band gap. All right, and this delta EV or delta EC is actually can be completely evaluated from the hybrid functional or GW calculations, not defective, not the defective the crystal, but the perfect crystal, and therefore it is much easier to calculate. So this is what we have done many years ago in this paper in our group. We have calculated this conduction band and the balance band shift when you are applying this hybrid functional, okay? And so using this balance and the conduction band shift, you may simply, fix this transition level and you can simply, the shift of the balance and the conduction band accordingly, okay? So that's one approximations. There are some other correction schemes, okay? So the first, once, long time ago, this was quite popular. This is the extrapolating using the DFT and the DFT plus U calculations. This means that in the DFT calculations, the band gap is small, and the DFT plus U calculations, actually we have not discussed it here, but this is necessary for the d-electron system, the insulating d-electron materials, and in this method, you can increase the band gap. And you simply, they have simply extrapolated this band gap correction effect, but this is does not cost much computational time, but this physical background is very fragile, and so it is not used anymore. Okay, but these days, these hybrid calculations, once it is implemented in the VASP calculations, many people are actually using this method to the correct this banding, or they calculate everything within the hybrid functional calculations. That is possible these days, and so this is one of the favored method recently, and maybe the most ab initio approach. You can combine this DFT plus GW calculations, for instance, in this the literature. This is very costly and there requires careful treatment on the self-dependence of defect level for the charges system. But once you can do it, then it will give you very accurate, in principle, very accurate defect level calculations. But it's very costly because GW calculation is much more expensive than even the hybrid functional calculations. Or maybe if you are not sure, then you can simply fix the balance band shift and you can simply push up the conduction band, but this is not recommended at all. All right. Okay. So maybe these days the method of choice would be using the hybrid functional calculations. But if this method is too computationally expensive, then you can actually use the relaxation energy or the geometry from the or the less expensive method like LDA or GDA calculations, and use the same geometry or the correction energy, and you repeat the calculations using these hybrid calculations in one shot. Then it will be much more doable. All right, and you can also calculate the magnesium vacancy, which is the also another vacancy that can be possible in the magnesium oxide. And this cation vacancy in ionic solid is called the V center. And but in this case, what you can find is that when you introduce this defect, there is very large relaxations around the defect site. This is in contrast to the oxygen vacancy. And also, there is no defect state in the band gap. So it is very clear. It's very similar to the clean, the perfect supercell. Okay. This means that the defect level is actually resonant inside the valence band or conduction band. And therefore, in contrast to the oxygen vacancy, which hold the 2 electrons, this magnesium vacancy does not hold the whole. Okay, so therefore, this vacancy site effectively charged as negative. All right, so that's why this relaxation around the defect is so large in these calculations. Okay, and also you can introduce this charge state, like in this case, not plus charge but the minus charge. Since you have the hole, you can increase the number of the electrons by 1 or by 2, and similar to single ionized or double ionized case. But the relaxation is quite similar, and so this is because the system is always effectively negatively charged, the same charge state. All right, so there's no defect level here. All right, but anyway, you can calculate the corresponding deformation energy of the V center. The same way, you can consider oxygen rich limit. In this case, your MgO is in touch with the oxygen to the pure oxygen gas. All right, and the magnesium rich case, your system is embedded into the magnesium, pure magnesium. All right, so what we need is magnesium chemical potential, which is in oxygen rich limit, this magnesium chemical potential is minus 7.7 electron volt, and the magnesium rich limit increases much higher, and this becomes minus 1.5 electron volt. Okay, and you can also introduce the charge correction scheme, but as you can see here, feeding is not good. And depending on this charge correction method, it does not converge to a one energy. And this is because the defect level is not localized. So the charge of the defect level is ill-defined. Right? In this case, such a delocalized charge state, this charge correction scheme usually fails or is not effective at all. Okay, so all those charge correction scheme is the best when you have the localized defect level. Okay, and this is the transition level diagram, both for the oxygen vacancy and the magnesium vacancy. Okay, so for the oxygen vacancy, we had this transition, and the magnesium vacancy, we have this transition. And you can see that in the case of the magnesium vacancy, all those transition level is concentrated, is near the balance band maximum. Okay, so this is actually related to the very shallow nature or resonant nature of your defect state. And this is oxygen leach limit, and this is a metal leach limit. Okay. All right. So and here we have considered this oxygen vacancy and magnesium vacancy, but in fact, in an MgO, interstitial defect, especially the oxygen dumbbell, is usually can be considered, and sometimes it is reflected in some literature. Also, the calculate on this oxygen dumbbell in the magnesium oxide. So yeah, but the problem is that for those interstitial defect, because of this large track hindrance, or your lattice actually relaxes much larger with such an interstitial defect, and so you needed to take a larger supercell to have the converged result. Okay, so there are some general remarks on the defect calculations, and especially on the shallow defect. So as I mentioned before, when the defect level is localized, then this computation is much straightforward and easier, and also the correction scheme works quite well. All right, but when the defect states are close to the band edge, like the shallow level, and their wave functions are usually localized over several nanometers, right? For instance, in the case of the phosphorus in silicon, if you look at the literature, then its wave function size is about 2 or 3 nanometer, or maybe the 5 nanometer, okay, which is really, really large. So in order to have the really, these correct calculations, you need to take at least 10 nanometers per cell, right? 1,000 angstrom, right? Which is completely impossible for the present calculations. But there is one group in IMS who had actually calculated how many, maybe 100,000 silicon atom calculations to have the correct the shallow impurity level of the phosphorus in silicon. You remember the paper? Yeah, 100,000 silicon atom. Yeah. So, but that is only possible for them. Therefore, so when you use for those very shallow level, when you use the small supercell, and this actually induces large dispersion because your defect level overlap between the cell to cell, between the cells, and therefore, rather than this flat band, which is reflected is localized, it is rather dispersive, right? It follows quite closely the dispersion of the balance band. All right. So in this case, you have the different energy level with the different K point, and therefore K point sampling would be very important. I have this problem in many times when you are calculating this very highly dispersive oxide materials like indium oxide. In that case, so this defect level, unless you have a really, really huge supercell, it is very dispersive. Therefore, for example, if you sample the gamma point where you have the lower energy, then it is very small defect formation energy. And it gives you lots of the artifact. It's very easily formed. So and the simulations will is quite weird. But anyway, so in order to have this, that you have the K-point sampling, and for the small gap insulators or the semiconductors in which the band gap is less than 2 electron volt, even though the defect level is well in the middle of the band gap, it is usually extended quite a long distance. In MgO, this band gap is quite big, so in this case, the wave function is quite localized. But for those semiconducting materials, even though the defect level is in the middle of the band gap, it is quite dispersive. Therefore, in this case, this charge and band gap correction may not behave so nicely as we have seen in this class. So in this case, KL cares are needed, or you simply need to the large supercell or systematic analysis on the chart, the supercell size effect. Okay, for the further reference, you may refer to these papers. All right, and also the shallow defect, one another the difficulty in shallow defect is that because it is so close to the balance band maximum, it can be sometimes sensitive to the functional. So for instance, we have seen that just before that, the V center in MGO was resonant. Okay, so the Fermi level is the below the balance band when you use the semi-local functional. But there is a literature that by making use of the hybrid functional, actually this V center gives you the localized state. Okay, so this is because the balance band when it is pushed down, then this resonant state is now becomes the higher than the balance band, and it now appears in the middle of the band again. All right. So this is hybrid functional calculations of the V center, and you can see that the whole state or acceptor-like state appears just above the balance band, and this wave function is localized around the vacancy. Okay, so for those shallow impurity, maybe it may be worth trying checking how the defect level behaves when the band gap is corrected. Okay, or most conveniently with the hybrid functional calculations, before you judge that it is really resonant or the shallow. Okay, and this is another comment that particularly for the covalent solid, the symmetry rolling Yantala distortion occurs. Okay, for instance, this is a silicon vacancy, all right, and it is known that for the silicon vacancy, these two atoms are actually there are 4 dangling bonds, okay, and these 2 atoms can get closer, okay, and originally it was tetrahedral geometry, but by these two bonds are getting closer, and this lower the symmetry, and this such a symmetry lowering distortion is called the Yantala distortion, and so by doing so, symmetry group is lowered from TD to the D to D. Okay, so but if you remove the one silicon from the calculations and you just relax it as it is, then because of the symmetry of the original system, you never find such a Yantala distortion. All right, so either you intentionally distort your system in this way, or maybe you can do the sum of the molecular dynamic simulations, or some amount of the some length of the annealing simulations at the elevated temperatures to obtain such a really symmetric lowering relaxation patterns. All right, so this is quite complicated matter. All right, okay, so there's and this transition level diagram is very useful in many applications, and is one of the things that I use frequently in my own applications. So basically, it gives you the ionization energy of the defect level. So for instance, if your defect have this energy diagram of that, this is 1 plus energy and this is neutral energy, then this neutral energy means that the 2 electrons are trapped at the defect site. And this energy, where 1 plus charged, but its electron Fermi level is conduction band minimum. So this is the configuration where you have 1 electrons are trapped at the oxygen vacant site, but the other electron is actually at the Fermi level. Fermi level is a conduction band minimum, so therefore the electron is at the conduction band minimum. All right. So this means that this energy difference, epsilon A, is actually energy then you excited this configuration into this configuration. All right. And this electron is at the conduction band minimum, so it is conducting. All right. And this energy is so-called ionization energy. All right. Okay. Or more specifically, thermal ionization energy. Okay. So this is the energy then you need to excite or activate your dopant. So in order to be the shallow impurity, which create carrier, this energy should be around the thermal energy of at the room temperature, like a 0.02 or 0.03 electron volt, okay, or less than 0.1 electron volt, okay. So so this is the ionization. This energy reflects the ionization energy of the defect, and also this is the in the case of the hole-like state, this is the energy to activate the this acceptor. This is the donor. And also, this energy gives you the concentration of the defect, okay? And from the basic statistical mechanics, by considering this entropy term and minimizing your free energy, you can obtain that your the density defect concentration is, is in general gives like that, or for simplicity, when the defect concentration is very low, then it is simply number of lattice site times exponential of the Boltzmann factor of the Gibbs free energy. Okay, so it gives you the concentration of the possible defect at the equilibrium. So using this formula, we can actually determine the charge formula level of your system from the charge neutrality condition. Okay, so total charge in your system has the when there are some amount of the electron carrier in the conduction band, it is minus NC. So NC is the electron in the conduction band, which is the integration of the dense state times the Fermi direct distribution from the conduction band minimum to the infinite. Okay, so it gives you the electron number in the conduction band, and also this PV. This is the hole in the valence band. It is the integration from the minus infinity to the valence band maximum of the dense state times the whole concentration. 1 minus F is whole concentration. Okay, so this is the electron and this is the hole, and also each defects are at a certain concentration. It is charged with the Q. Okay, so you in sum all the possible defect type and charge state, then it will give you the total defect and the charge state. Okay. All right. So by adding up all of these, you have the total charge in your system. Okay. And since the charges in the Berg material is usually should be the neutral, right? It is if it is charged, it will cause you an extremely large amount of the energy. Therefore, it is effectively almost neutral. Therefore, you can impose this condition of the charge neutrality by setting this to 0. Okay, so what is the parameter in this equation? The parameter is that the Fermi level. Okay, so the Fermi level controls the occupancy of the electron in the hole. Okay, so it controls the NC and the PV. And also, from the previous discussion, the Fermi level affects the formation energy of the charge defect. Okay, therefore, the concentration, which appears here. All right. So this whole equation has the one parameter of the Fermi level. So by changing this Fermi level, you can find the one Fermi level that gives you exactly 0, right? And that is the Fermi level of the of your system, which is the intrinsic Fermi level. Okay. And also, of course, it depends on the temperature. So by changing the temperature, you have the different the Fermi level. Okay, so for instance, if your Fermi level is, or the formation energy is like this, 1 plus and the neutral, then your Fermi level should be around here. Why? Because at this Fermi level, we have a certain amount of the electron at the conduction band. From the valence band is so far away, so there is no hole, right? It is has some amount, but this is the Fermi level is close to conduction band, the minimum. So there are a certain amount of the electrons, which is balanced by +1 charging. Okay, it is here. If you push up your Fermi level, then you are reducing the plus charge, but you are increasing the electron, which can break the neutrality condition, right? So in that way, the Fermi level is uniquely defined here. All right, and so and as a result, you have the electron carrier here. So that's why this type of the transition level shape is called donor. It is donor type. It creates electron. On the other hand, if your transition level goes like that, okay, so flat and it rapidly goes to the minus charge state, then in this case, Fermi level should be located here. Why? Because at this Fermi level, we have a certain plus charge hole here, and also which is counterbalanced by the minus charge of the defect. All right. So you have a certain amount of the hole. So that's why this is p-type level. Okay. All right. So you can calculate this the density, defect density of the whole electron, and also each charge state of the defect. Okay, of the oxygen vacancy and the magnesium vacancy, and all this, and then this diagram is called the Shockley diagram. Okay, and this is the with respect to Fermi level, and here you can add up all the negative charge, which is indicated by this blue line, and total negative positive charge, which is indicated by this red line. Okay, and it crosses one point. Okay. And by imposing the charge neutrality, you can see that this is the intrinsic Fermi level. All right. So in this magnesium oxide, the Fermi level is slightly close to the conduction band rather than the valence band. And also, by changing this oxygen chemical potential in terms of the partial pressure, this is 10 millibar. And the right figure is the 10 to the minus 8 millibar. This is UHV condition, ultra high vacuum condition. And you can see that this is the very oxygen, the rich condition. Therefore, it is like more like oxidizing condition. And so you have the this hole carrier a little bit, and electron carrier, which is far larger than this electron carrier. Okay, and okay, so and this is the which is the comes from this negatively charged. This hole comes from the negatively charged of the magnesium vacancy, especially magnesium 2 minus. And also, and on the other hand, by reducing the oxygen partial pressure down to the 10 to the minus 8, you are actually providing the less, or am I right? 10 millibar. Okay, you are reducing this oxygen partial pressure. So this is a little bit more oxidizing condition. Okay, so therefore your whole concentration is just decreased a little bit. Okay, so you can understand that by reducing the oxygen partial pressure, you are decreasing the whole carrier. Okay, which is quite reasonable, and you can understand that from also data appears in the numerical calculations. All right, so therefore this defect calculation gives you the carrier type, whether it is hole or whether it is electron, and also by controlling this oxygen partial pressure, you can estimate how much carrier you will generate by growing your sample at a certain oxygen partial pressure. Of course, by assuming the equilibrium condition. And also, this transition level diagram, you can get this optical absorption energy. But here, one thing that you have to remember is that, for instance, if there is a defect, then this photon is observed. Then one of the electron, by observing these photons, it is excited into the conduction band. There is a photon absorption of by this defect level. But one thing that's different from this previous calculation is that this absorption occurs so instantly. Photon absorption occurs so instantly that in this excited configuration, the atomic geometry is still the same as this neutral state. Because this photon absorption is much shorter than atomic motion, and therefore when it absorbs it, the electrons goes up, but the other atoms, ions, do not have enough time to respond. And so in this configuration, the energy is actually, no, the configuration is the same as the neutral state. All right? So on the other hand, in the previous case, for instance, when we calculated this, this configuration here, we have relaxed with +1 charge state, right? You remember that this 1+ charge was calculated by relaxing everything, right? So this is why they call it a thermal ionization energy, right? It's thermally equilibrated. However, when the photon is observed, the atoms cannot respond so quickly, and therefore atomic configuration is the same as the neutral defect state, right? So, and that is the so-called the Franck-Condon principle, and this is the classical version, so that when a photon is observed or emitted, the ions are frozen while the electrons are relaxed. Okay, so this is Franck-Condon principle. So therefore, for instance, in the neutral configuration, you have this. This is the x-axis is the mechanism displacement, and y is the formation energy. So in the neutral state, you have this energy diagram with respect to the mechanism displacement. But when this photon is observed, then it becomes a 1+ charge state. So thermally, it should go up. Okay, so from this state it goes to, and this configuration should go to this configuration. However, this photon, according to Franck-Condon principle, this mechanism does not move. Therefore, which means that it becomes a 1+ charge, but still the ion is fixed at this original neutral configuration. In this case, the energy is a little bit higher than the relaxed configuration. Therefore, this absorption occurs at a higher energy than expected from this thermal excitation. Okay, which becomes the 4.5 electron volt. And also, when this +1 charge state absorbs another photon, and it becomes 2+ charge state, then the configuration. Okay, so after absorption of the first photon, then atoms are relaxed into its own equilibrium position, and it goes like that. And when it observes the second photon, then it excites to the 2+ configuration, but still the configuration is fixed to the +1. Okay, so this is the photon absorption. On the other hand, when it emits the photons, for instance, from the 2+, and it observes, right, 2+2. Okay, when this the electrons at the conduction is captured by the defect and emit the photons, this photon emission, then the configuration is fixed to 2+. And here, and the second photon is when it's emitted, it is the fixed to the plus charge. Okay, so by just simply fixing the atomic position, you can calculate those energy of the photon that correspond to photon absorption or photon emission. Okay. Okay, this is actually the last slide, but I still haven't. It's okay. Okay, so this is actually a slide I have rushed it too quickly. Yeah, and also we can use this formation energy diagram to calculate the space charge distribution at the interface structure. For instance, in a metal insulator interface, you may know that this band is actually bending, right? Such that this metal Fermi level becomes equal to the Fermi level or intrinsic Fermi level of the insulator, and is away from the interface. So this band bending is very important parameter that defines the performance of the electronic devices. And here, the band bending, the band bending is determined by the space charge develops when this Fermi level is deviated from the intrinsic Fermi level. Okay, so what do we have calculated just before is that, for instance, the Fermi level, when the Fermi level is here, is charge neutral, but when the Fermi level is is below this intrinsic level, then you can calculate from the difference. You can calculate how much charge will be accumulated in those regions. Or when this Fermi level goes higher, then these electrons will be accumulated. Okay, so this diagram gives you that amount of the charge that develops when the Fermi level is away from the intrinsic level, and so and by combining this with the electrostatic Poisson equation, you can calculate this band very accurately. Okay. All right. So that's the end of this theory session. That we have seen that in a defect, the defect level is developed, and it can become charge state, and it can behave, and we can affect the electrical property and optical property, and you have learned how to calculate those carriers for the photon absorption and emission spectrum from this transition level diagram. Okay. All right. So that's the end, and I just welcome to the question or the comments. So any question in the from the SNU side? Any volunteer? So in SNU side, you can ask question in Korean, then I will interpret in English. That's fine. Doyeon, are you sleeping?
Yes.
Yes, you're sleeping.
No. Any questions?
Okay. If not, then okay. Let's close today's lecture. Okay. And so next week we'll practice we will follow this example in the MGO. Okay, using this the script that not the script but the info files that we prepare. Okay. So the computation is going to take a little bit more time because it's a defect calculations. All right, the next time. Okay. All right. Okay. So it is very nice to see you here. Okay. And if there's any question, you can contact me at any time with any way. Okay. Yeah. Okay. Thank you.